Welcome to Life with David. I'm David, and today I'm continuing my research into the programmable input-output features of the RP2040. Recently, I've been using a Raspberry Pi Pico to create waveforms. This time, I want to use the Pico to make music using MIDI, the ubiquitous 1980s technology. I've always wanted to get into the gory details, so why don't you join me as we explore the musical instrument digital interface? In the early 1970s, music synthesizers were making their way out of university labs and into the hands of musicians. As a variety of companies brought this new technology to market, there were lots of innovations, but little standardization. In 1978, microprocessor-based synthesizers were added to the mix, and their capabilities increased significantly. Several companies, including Sequential Circuits and Roland, were concerned that a lack of compatibility between digital synthesizers might limit their use, which could ultimately hurt future sales. So, in 1982, they spearheaded the development of the initial MIDI spec, which was a way that musical instruments could communicate with each other. This spec was a serial communications protocol running at 31.25 kilobaud, a set of basic instructions for controlling the instruments, and optical isolation circuitry to eliminate ground loops. By the end of 1982, the Sequential Circuits Prophet 600, the first synthesizer with MIDI, hit the market. The Roland Jupiter 6, also with MIDI, followed shortly thereafter. In early 1983 at the NAMM show, a Prophet 600 and a JP6 were connected together for the first time, and the interface worked. Each keyboard was able to play the other's synthesizer. Over the next few years, other manufacturers adopted the standard, and the instruction set grew to encompass other specialized control features. In fact, the standard met the needs of the music industry so well that it was revised for the first time only a few years ago. I played with MIDI a bit starting in the mid-1990s with a generic Sound Blaster card in my Packard Bell computer. However, I used the internal connections to control the card because I never had a musical instrument that had MIDI. But now, I have this awesome Yamaha Tyros keyboard with 2 MIDI connections and a Raspberry Pi Pico, so I'm ready to make some music. How does MIDI work? Musical instructions are transmitted between devices. The instructions include things like the pitch of the note, the voice, the loudness, the attack, and many other parameters. A computer can control a digital keyboard, or a computer can record information from a keyboard. Many other devices, such as drum machines or sequencers, can also be connected. We'll get into those details shortly. Standard MIDI cables consist of shielded 2-conductor cable terminated by 5-pin male DIN connectors on each end. Information only travels in one direction from the MIDI out connector on one device to the MIDI in connector on the other. The cable completes a current loop where plus 5 volts on the transmitter produces no current and represents a mark. Ground creates a current in the loop and represents a space. The signal is in a marked state when it's idling. To eliminate the interference that ground loops could cause, there's an optical isolator in the receiver, and the shield is only attached to the MIDI out instrument. A single MIDI cable can carry up to 16 channels of MIDI data, each of which can be routed to a separate device. MIDI data uses an asynchronous serial signal at 31.25 kilobits per second, including 1 start bit, 8 data bits, and 1 stop bit. 1 or more bytes make up a MIDI event, which can define a note, adjust timing, or control the operation of a MIDI device. Let's start out by looking at the simplest MIDI event, defining a note. In its most basic form, this event takes 3 bytes. The first byte actually consists of 2 half bytes or nibbles. The most significant nibble specifies the instruction, in this case 1001 for note on or 1000 for note off. The least significant nibble specifies the channel, from 0 to 15 decimal. The second byte is the pitch of the note, from 0 through 127 decimal. Middle C on a piano is 60 decimal, or 3C hex. The third byte is the velocity and varies from 0 to 127 decimal. 0 will turn a note off, 127 is very loud. Let's look at how this is implemented in the real world. The first thing I'll do is to wire a MIDI receiver and transmitter to my Pico. Since MIDI operates at 5 volts and the Pico GPIO is at 3.3 volts, we need to add a level converter into the circuit to keep things from blowing up. I'll use the same one I used in a previous video. I'll put a link in the description below. I connected 2 MIDI connectors to the level converter. I put a link to them in the description. Note that the numbering of the pins is not sequential. Refer to the picture here. Only pins 4 and 5 are used by the MIDI signal. The only other connection is the shield, which is connected to the ground of the transmitter using pin 2. Note that pin 2 on the receiver is not connected to minimize ground loops. Initially, I used an H11A1 optocoupler from my junk box for the MIDI receiver. Unfortunately, that didn't work well. The signal was too weak and noisy. So I ordered some 6N138 optocouplers that have become the de facto standard for MIDI work. They work much better and I got a nice clean, clear signal. Let's take a look at the output of the Tyros. I connect a MIDI cable from the MIDI A out port on the Tyros to the input on my circuit. I'll use my Handtech scope in decode mode set at 31.25 kilobits per second. I'll measure the signal at the input to the level converter. I keep pressing a note, but I'm having trouble getting the scope to trigger consistently on the key press. I keep seeing a single byte, FE hex, transmit about every 200 millisecond, which is making it hard to grab the key press. It almost looks like a watchdog timer, so I dug into the MIDI spec. Sure enough, that signal is called active sensing, and if it's implemented, is supposed to be transmitted at least every 300 milliseconds when no other active MIDI signals are being sent. If the receiver fails to see that signal, then it will assume that the MIDI connection has been lost and will initiate shutdown procedures. Finally, I got a good capture. Let's look at the message. As we look at the bit stream, note that the least significant bits are being transmitted first. Here, 2 channels, 0 and 1, which represent 2 different voices, are playing at once. The first byte turns on a note in channel 0. The most significant nibble, 9, is the turn note on command. The least significant nibble, 0, is the channel number. The second byte identifies the pitch of the note, here 3E, hexadecimal. The notes range from 0 to 7F hex, with 3C hex being middle C. Therefore, 3E is 2 steps above middle C, or D above middle C. The third byte specifies the velocity, or how hard the note is being played. In this case, the velocity is 2D hex. Since the maximum velocity is 7F hex, 2D hex is between pianissimo and piano, or very quiet. The command is repeated for the same note in channel 1. Now I'll release the key. Here the commands are the same, except the note is turned off by using a velocity of 0. Another way of turning the note off is to use a starting nibble of 8 instead of 9. In this case, the first byte of each MIDI event would be 8-0 or 8-1. I think I know enough to try programming a note from the Pico to the keyboard. I'll start by putting together a very simple program which is based on the UART program presented in 3.6.3 of the RP2040 datasheet. I modified the program a bit, so I'll quickly explain how it works. Because MIDI is timing critical, I'll be using C, C++, which is faster than MicroPython. When using PIO and C, C++, there are 2 programs, a main C program and a separate PIO program. The PIO will take the MIDI data from the main program and format it and transmit it serially at 31.25 kilobits per second to the MIDI transmitter hardware through GPIO 0. The PIO state machine clock frequency is set to 8 times the baud rate, or 250 kHz. This means a bit must be output every 8 clock cycles. We'll map both the out pin 0 and the side set pin 0 to the transmit GPIO pin. The side set will manage the start and stop, and the out will handle the actual data. The PIO program starts by specifying that we will be using side set and that it's optional. That steals 2 bits from the potential delay for each PIO instruction, but that still leaves us with 0 to 7 clock cycles of potential delay. Here the side set is set to 1 while waiting for data from the transmit FIFO. When data is present, it will pull the data into the output shift register. If data is immediately available from the transmit FIFO, the instruction will still take 8 clock cycles, 1 for the instruction and 7 for the delay. This provides the proper length stop bit. After the data is loaded into the OSR, the X scratch register is preloaded with 7 and the side set is cleared to 0, which will define the start bit. This statement will also take 8 clock cycles. After the start bit, PIO enters a loop where out shifts 1 bit from the OSR to the transmit pin. Then it delays 7 more clock cycles while decrementing the X scratch register. When the X register reaches 0 after all bits have been transmitted, the program jumps back to the top where the stop bit is again set. Now let's move to the instantiation part of the PIO program. This is a helper function that the main C program will call to instantiate the state machine. Here we pass the PIO instance, the state machine number, the offset of the PIO program, the number of the transmit pin, and the baud rate. For more information on how the helper function works, please see PIO episode 7. I'll put a link in the description below. This initially sets the transmit pin to 1, and this sets the transmit pin direction to out. Here we have to initialize the transmit GPIO pin for the selected PIO instance. We only have to do this if we're using the GPIO pin as an output. This grabs the default configuration and assigns it to this PIO. We'll modify it below to get the final configuration. This sets the OSR to 32 bits long and shifts right, the least significant bit being first. This statement maps 1 out pin to the transmit pin. Here we'll also map 1 side set pin to the transmit pin. As we mentioned before, this allowed side set to control the start and stop bits and the out pin to handle the data output. Since we don't need a receive FIFO, we'll increase the size of the transmit FIFO to 8 words. This could save a little wait time during multiple note operations. This calculates the clock frequency as 8 times the baud rate. And this sets the state machine clock cycle to the calculated clock frequency. This actually pulls the trigger on instantiating the state machine and the configuration. And this will start the state machine. This function will write a word of data to the state machine's transmit FIFO, blocking it if the FIFO is full. And this function is called by the main C program and will transfer an unsigned integer array of MIDI data to the state machine using the previous function. We only transmit the 8 least significant bits, but the data word is 32 bits long. We'll use 100 hex to signify the end of the MIDI event. As our first test, we'll turn on and turn off a single note repeatedly to the Tyros. We'll use the note on and note off instructions. We'll include the usual libraries and also the PIO program we just wrote. In the main program, we'll assign the MIDI event array, in this case 4 words. We then load the MIDI instructions into the array. The first is the instruction to turn a note on or off. The most significant nibble specifies the action, 9 hex turning a note on and 8 hex turning a note off. The least significant nibble specifies the channel, in this case 2. The channel number can be confusing. MIDI starts numbering at channel 0. However, many, but not all, keyboards start at channel 1. That's the case with the Tyros. The second instruction in this MIDI event is the pitch of the note. Here we're specifying 3C hex, or middle C. The next instruction is the velocity of the note. This time we're specifying 7C hex, or fortissimo, which is very, very loud. This is the end of the MIDI event, so we'll enter 100 hex to signal the end to the PIO program. Now we'll assign the PIO instance as 0, set the state machine as 0, reserve the PIO program and capture the offset for later use, and then we'll call the helper function to instantiate the PIO program. Now we'll just enter an infinite while statement where we send a MIDI event every 200 milliseconds, just cycling between note on or off. Let's try it out. First, I'll swap the MIDI cable to run from the output of my circuit to the MIDI A in on the Tyros. Then I'll compile the program and load the UF2 file into the Pico. Success! The result is what we expected, a very annoying note repeating about every half second. We should also be able to use note on and simply set the velocity to 0 to turn a note off. Here I try a similar program. I'll just cycle between a velocity of 7C and 00 hex. Good, that works also. How about playing 2 notes at the same time? Here we'll define a longer MIDI event matrix and put in 2 3-instruction strings to play middle C and the E above middle C. It looks like that works also. Now let's try it with 3 notes. Again, success. How about if we play all the notes available? The program is similar, except every time after we turn a note off, we increment the note pitch by 1. When we reach the highest pitch, or 7F hex, we'll start at the bottom again. Okay, that's cool, but not very musical. How about if we try to play a song? There's a standard MIDI file format that's all-inclusive, but I'm not going to try and tackle that at this time. Instead, I'll put together a simple list of notes and then press a button each time I want to play the next note. Let's go through the program. Here we'll include the standard libraries, including the standard I/O, because I want to be able to print out the note to a terminal. I'll define the button as GPIO 15. I'll initialize the I/O package for the terminal output. I'll initialize the button, set its direction as in, and pull the input level up. I'll set the MIDI out pin to 0 and set the MIDI baud rate to 31.25 kHz. This array contains the notes for a simple song. I use 00 at the end of the song to indicate the end of the file. The velocity and end of the MIDI event will not change during the song, so I'll assign them here. I'll initialize the variable sequence that will count through the notes of the song. Next, we'll instantiate the PIO just like we did in the previous program. Now we enter a loop where we wait for the button to get pressed. Once the button is pressed, we enter a loop where the song is played. First, we check the note pitch. If it's 0, we reset the sequence counter to 0 to start playing the song again. We load the turn note on instruction into the first byte of the MIDI event, and then we get the note pitch using the variable sequence to load it into the second byte of the MIDI event. Then we pass the array containing the MIDI event to the PIO. This loop just wastes some time waiting for the button to be released. When it's released, we load the note off instruction into byte 1 of the MIDI event and send the MIDI event array to the PIO again. Finally, we increment the variable sequence so we can get the next note in the song array. Okay, let's try it out. Pretty catchy, huh? I think this is a win, at least for now. Thanks for joining me today. I know that the Tyros has an impressive ability to synthesize and play music on its own. However, I get a certain satisfaction from being able to at least tickle some of its capabilities at the lowest levels. We were able to make some simple music using a Pico and the Yamaha Tyros. This video rekindled my interest in this vintage standard, and I'm interested in exploring MIDI files in more detail. Depending on what I learn, I might make another MIDI video. Let me know what you think. If you like this video, or you think someone else might, please give it a thumbs up. If not, give it a thumbs down. The more likes this video has, the more YouTube will recommend it to others. Also, please leave a comment or suggestion for things to do. I hope to do more of these videos, so please subscribe and click on the bell for notifications of new videos. Let's get together next time for another day in Life with David. See you soon!